this homework, I'm just going to make it due. All the homeworks are now just going to be due on the day of the final. Yeah, the last part was kind of tricky because I mentioned all the extra negatives could have made it confusing. Okay. Alrighty. Now, I want to take a look here at the new technique that I was mentioning here that's going to help us deal with more complicated integrals. Now, before we do that, though, I just want to recap some of the formulas that we've seen so far for the integrals, the antiderivatives. Now, notice that these rules that I'm giving you here, they're looking a little bit different from the formulas that we've seen in the past, namely because now I'm talking about the variable being u rather than x. So the formulas here have a u and a du. And I'm doing that for a reason. I prefer this version of the formulas, and you guys are going to see why in a second. Maybe more on Monday too. All right, but remember though, in general, the power rule for antiderivatives or integrals was following. If you have the integral from u to the r du, then okay, we just add 1 to the power and divide by that. Now these ones here are indefinite integrals. They don't have any limits of integration. That's why we're back to adding a c. Now the other rules that we saw before was in the case for logarithms, if we have a 1 over u du, actually this is the first time that we're seeing it from, no, we've seen it before. If we have the 1 over u du, then it's the ln of the absolute value of u, namely because the natural log does have a restriction in its domain. You cannot take the log of a negative number, so that's why we have the absolute value there, plus c. Now, in the case where we know that the u is greater than 0, then that's fine. You can just avoid the absolute value. And last but not least, we have the integral of e to the u du is simply e to the u plus c. And again, this one's kind of easy because the derivative of e to the x was simply e to the x, so that's why the integral of e to the u takes you back to the e to the u. Nothing changed. Okay, so let's try a couple of problems here. So for this one, I want to begin with a relatively easy problem, just the integral of x to the 7 dx. Okay, so taking a look at this problem, it seems like, oh, it is just a power rule. So the way that we would find the integral here is simply going to be x raised to the 7 plus 1 over 7 plus 1 plus c. So this gives us the x to the 8 over 8 plus c. And again, the nice thing about derivatives and integrals is that we can always check them. So if I choose to check it, I can just take the derivative and see if I'm back to the x to the 7. So if I take the derivative of x to the 8th over 8 plus c, then we simply bring down the 8, take away 1 from the power, and the whole thing was being divided by 8. So you see that, oh, we indeed get the x to the 7, and the derivative of c was 0. So yeah, we do get the x to the 7th. Checks out. Okay, so this one here, hopefully, was a breeze. Nothing too bad. But now let's take a look at the other integral, though. Now notice that this one here, it seems like we have an inside function, and we're raising it to the 8th power. Now, if I ask you to take the derivative of 3x minus 4 to the 8th, then you would be thinking, oh, okay, well, that's kind of looking like a chain rule. But we really haven't seen any techniques involving like the chain rule with integrals. Is there an equivalent? Not exactly, but what we're going to be doing now, it's basically the closest thing to the equivalent of the chain rule with integrals. So let's see here. Now let's say that we're not too sure, but we simply go ahead and attempt to use the power rule for this one. If we use the power rule, then we're simply going to be getting here, let's see, if we use the power rule, that's going to be a 3x minus 4. And well, put the integral here to the 8dx. That's going to be equals to a 3x minus 4. We add 1 to the power, so it's going to be a 9. Divide by that. And we add a c. Now, okay, I mean, it doesn't seem like a bad idea, but if we go ahead and check it, let's see. If our quote unquote guess seems to be giving us good results, because if we get the derivative and the derivative matches this, then we're good. So let's see, what is the derivative of the 3x minus 4 raised to the 9 over 9? All right, so I'll use the chain rule. So we're going to have here, let's see, the derivative using the chain rule. Remember, it's a derivative of the outer function. So we would bring down the 9 times the inside, which stays the same. Take away 1 from the power. The whole expression here was being divided by 9. So we can cancel this. Okay, so it's looking good. Is this derivative good though, or are we missing something? If we're thinking about using the 3. So we were close, but not quite there. Because this is equals to 3 times x minus 4, 3 times 3x minus 4 to the 8th. So we managed to get this right here, but we got this 3 here that's basically messing up our guess. It's not quite there. It's very close though, not quite there. All right, so we're gonna need a new technique to perform this type of integrals. Now, before I show you guys this technique, I want to talk about a concept known as differentials. Now, we didn't really cover differentials in this class, so I'll just tell you essentially what a differential was. So when we were talking about derivatives, well, I'll let you guys copy this, I suppose, but when we were talking about the derivatives here, we had, oh, the derivative of y with respect to x is the equivalent of f prime of x, right? Nothing crazy there, nothing new. dy dx is the same thing as f prime of x. Now, when we're dealing with the concept of differentials here, we're basically assuming that the dy and the dx, remember the d was representing a change. So we're saying that with differentials, we can assume that the dx, the change in dx, is small enough that we can actually calculate the change in y produced by that small change in x. But again, if I'm saying that dx is a number, we can treat it as a number. So in essence, we can go ahead and multiply by a dx on both sides to get the dy by itself. So we would get dy is equals to f prime of x times dx. And this is what's known here as the differential. Again, we're not going to be talking too much about them, but we are going to be using this concept of, hey, we can get the dy by itself by multiplying the derivative times dx. And this is what we're going to be using because it's going to help us handle the other integral problems. Okay, so let's practice a little bit here with the concept of a differential. And this problems, I'm basically going to ask you guys to find out, hey, what would be the dy? All right, so remember here that basically the dy is just going to be the derivative of the function times the dx. Let's put the dx in black. Okay, so we are given the function f of x is x cubed. So what would be the derivative of x cubed? Let's put here dy is equals to the derivative of x cubed should be a 3x squared times dx, and that's it. We did the differential. Okay, now for more practice, what would we get for this one? Let's see. Again, remember, it's just still the derivative times dx. Now, what would be the derivative of e to the x squared? Well, that one maybe not so easy. Not too hard, but not too easy either. It's going to be an e to the x squared. But we are missing something. Let's put here. Yeah, recall that the derivative of e to the u is going to be e to the u times the derivative of u. So here we have the, in this case, this is our u. So we have e to the u times the derivative of the u. All right, and there we go here. We get the dx. Okay. Now let's try one more here, and let's go for example 4. So basically, in this case, if I just tell you, if we have u equals to g of x, which is the ln of x, let's go ahead and find du. Let's copy it here. Now this one here it might look a little bit different because in this one, I was telling you, hey, here's the f. In this case, though, I'm basically giving you the u is the g of x. So if we wanted to find the du here, then you would say that, okay, well, then the du is simply going to be the derivative of u times dx. Because again, basically with the differential, if we're saying that, oh, du dx, if that's the same thing as u prime, then to get the du by itself, we would multiply here by a dx, and that's how we get the du. And this is more in line with what we're going to be doing in a second. So if we want to find out, okay, what would be the du? we'll say here that the du is going to be equals to the derivative. Well, if u is the ln of x, what is the derivative of the ln of x? Anyone remember by any chance? It's going to be a 1 over x. All right, so we'll just put here a 1 over x times dx. All righty. So now we're ready to take a look at our new approach. And basically, this new approach, again, known here as the method of substitution. Just go to here. So this is going to be our goal. The goal for the method of substitution is to rewrite the integral in terms of u and du. So basically, guys, once we're given an integral, if it's looking too complicated, what we can do is simply change the variables. Rather than having an x and a dx, we're going to be having a u and a du. And typically, that's going to simplify the problems quite a bit. And I'm going to show you probably like 2 or 3 examples. No, maybe just 2. All right, so basically what I mean by this here is, let's say that I gave you the integral for some function of x times dx. We're going to be rewriting it here as the integral for some function of u, so this one here, times du. So that's going to be the key. So let's see, how do we do that? Let's go back to the integral that we just tried, and we got close to solving, but not quite there. Now, the reason that I was saying that this one here is the closest thing to the chain rule is because this is essentially telling you the integral of a derivative that you got with a chain rule. So when we were doing the chain rule, remember, we identified the inner function, which we typically call the u, and then we said, oh, then once we get the u, then we need to get the derivative of the u at some point and multiply it out. But when we're doing with the integrals, we still need to find out the u, but we're only going to be figuring out the u so we can rewrite the problem. But we're always still looking for the inside function. So if we have this problem, the integral of 3x minus 4 raised to the 8th power, it seems like the inside function is the one that's inside the 8th power. So we can define this one here to be the u. So first things first, defined the u, which again is basically going to be the inner function. Okay. All right, so now that we established the u, this one here was 3x minus 4 raised to the 8th. Then the next thing here is going to be to get, or just find, the differential du. And again, remember that the du was equals to u prime dx. All right, so in this problem, we get du is equals to, oops, sorry guys, my bad. Get rid of the eighth. Sorry, I got distracted. Get rid of the eighth on the u, because remember, we're saying the u is the inside, and the inside was 3x minus 4. So I was looking at the time, and it looks like we're only going to be able to do one problem, but it's fine. Okay. Alrighty. So the u, the inside function, was the 3x minus 4. Then that the u is now going to be, okay, what is the derivative of 3x minus 4? Which is going to be a 3, right? So we get 3 times dx. Now, since we're learning it here kind of for the first time, I'm going to add an extra step here. And once you find the du, and I'll just put it here 2.8. So for 2.8, solve for dx. Okay, so for this one here, if we solve for dx, then put it here, if we had du equals to 3dx, I'm going to divide by 3 to get the dx by itself. Divide by 3. So so we get here a dx is equals to du over 3. All right, so now that you've done this, you are about 60% done. But we're pretty good because this is the tricky part. All right, so the third step is now to rewrite the integral by substituting du and du, or sorry, dx. Because technically we already found what the dx is right here. So let's see. If we started off with the integral of 3x minus 4 raised to the 8th dx, notice that right now we said that, hey, this 3x minus 4 was our u. So this is the integral of u raised to the 8th power. Okay, so we replaced the x's now with the u, but now I want you guys to replace that dx here. Say, hey, you know what? Well, dx was the same thing as du over 3. So I'll just put it here, du over 3. Now you have an integral that only has u's and du's, no x's. I mean, there's a 3 right here that's dividing. I'm just going to take it outside the integral because, again, it's a constant. And remember, the constants, we can always just bring them out. So I'll leave it here as the integral, or 1/3 times the integral now of u to the 8th du. And notice here, guys, this integral, once we rewrite it, it is a much easier integral. Now, rather than integrating with respect to x, and that's why it's so important to write down the du or the dx, because we want to know which variable are we integrating with respect to? What's the antiderivative that we're looking for? So now, if we have 1/3 times the integral of u to the 8th, then we can say that our answer then is going to be 1/3. Then we apply the power rule and say that, okay, now we're going to be getting a u to the 9 over 9 plus c. And last and final step, whenever we make a substitution, we now go back to the original variables, and we're going to get here a 1/3 times the u, which was 3x minus 4, to the 9th plus c. And this was, oh yeah, thank you. Yeah, over 9. Now, let's take a look. How does this compare to our first guess? Remember that the first guess had an extra 3 right here. Well, this extra 3 would have been canceled now by this 1/3. So now we would have gotten the original integral or integrand. Okay, so this is the method of substitution. The key is to first identify the inner function. Sometimes you might pick a wrong inner function. It doesn't matter. As soon as you're working on the process, you'll find out that, hey, this integral is not working. If you made a mistake, you'll see that you have like an x and a u. It doesn't work. You must have only one variable. So if you are having extra x's somewhere in there, then pick a different u value. But once you get the u, you need to get the du, which is just the derivative of the u that you found times dx. Then solve for dx, so you can substitute them back in the integral, and you can get an integral only in terms of u and du. Now, this is where we're going to be stopping here, guys. But on Monday, we're going to be taking a look at a couple of extra examples here. Alrighty. So, yeah, this is it for today, guys. Now, the last topics that we're covering on Wednesday had to do with the u substitution. And again, the u substitution, the whole goal was to rewrite the integral in terms of functions u and du. That's the goal of it, because once we do that, we actually turn the integral into something that could be looking pretty nasty, into something that looks much easier to solve. And we saw this one example here where we have the integral of 3x minus 4 raised to the 8th. Now, as we did the u substitution, it ended up becoming the integral of u to the 8, much simpler than this. And again, that's usually going to be the case. To recap here, the very first thing that I want you guys to do when you're doing integrals of this kind is define your u. Very similar to the chain rule, the u was the inner function. So you define the u. Then we use differentials here, where we find the du, which is simply u prime times dx. So you get the du, you solve for dx, and once you find your u and the dx, then you substitute into the integral, and that should give you only an expression with u's. So this is basically going to be the main focus of today. So let's practice with a couple more integrals. And let's begin with this one here. So we want to find the integral of the following. It is the integral of 8 plus x cubed raised to the 5th times 3x squared dx. Right here, there we go. Okay. Alrighty, so for this integral, again, we go ahead and define the u. So if you were to see this integral, what seems to be the inner function? Well, kind of looks like I have an 8 plus x cubed raised to the 5th. So this is a pretty good choice for the u. All right, so first things first, we define the u. Okay, so u is equals to 8 plus x cubed. All right. Now, next step here is to find the du. And again, du is equals to the derivative of u times dx. Okay, so in this case, it looks like our du is going to be what? 3x squared dx. And the extra step here that I mentioned was to solve, what did I call it? Yeah, to a. Yeah, we solve for dx. So if I want to get dx by itself, it looks like I would need to divide by a 3x squared. Divide by 3x squared. So dx is equals to du over 3x squared. Okay. All right. So we defined the u, we defined the dx in terms of du, so we can substitute it in. And now let's see how our integral is going to change once we put in the new variables. So we're going to have here the integral. And I'll write the original, I suppose. Originally, it was 8 plus x cubed. Raised to the 5th times 3x squared dx. Once we rewrite it, then we have the u to the 5th times 3x squared. Now I'm going to substitute the dx here. So we're going to get a du over 3x squared. And here's the key. Once we make the correct substitutions, notice the x squared cancel, the 3's cancel, and we're left with the integral of u to the 5th du. Now look at that. This one here is much easier than the original. Now, before we continue, I don't know if there's any questions here so far, because this is the most important step, rewriting it in terms of u. Because once you do that, then it's just a matter of finding an antiderivative. Okay, so let's just go ahead and find the antiderivative. This is going to give us a u to the 6th over 6 plus c, which we proceed into the last and final step. And just basically go back to the original variable. So we're going to have the u, which was 8 plus x cubed raised to the 6th power all over 6 plus c. And this is basically our last and final step. At the very end, why did I rewrite it? Oh, it's basically because technically this problem was in terms of x. So once we perform everything that we can with the u, when we solve it, we always just go back to say, okay, yeah, this problem, the u was only helping us to manage the problem, but once we're done, yeah, we need to go back to the original variable. Okay. All right, so let's take a look at this next one. Somewhat similar problem. We have the integral for 2x times x squared minus 7 raised to the 6th. And I'll let you guys get a head start for this one. So what's going to be the u that would probably work in this problem? What's going to be the du? And what is going to be the dx? Alrighty. So let's see. Mireya, what would be the u in this case?
It'd be x squared minus 7.
I like that choice. Let's see. So our u prime going to be what? 2x dx. All right. So if we solve for the dx, divide, it looks like we'll be getting a du over a 2x. Okay. So we got the u to du again. This is how we're starting, the most important step, because that's what allows us to substitute it in. So then see, this integral is now going to become 2x times our u. Just put it here, times u to the 6th. Substitute in the dx. So we're going to get there a du over 2x. And very good. The 2's cancel, the x's cancel. So then we're left with the integral of u to the 6th du. And again, guys, the whole purpose of getting a du is so that we're able to perform the integral. If you have a u dx, that doesn't work. Or if you have a x u du, doesn't work either. You must have only u's and du's, no mix and matching between the variables. All right, so this one, the integral should give us u to the 7 over 7 plus c, which at this point we're pretty much done. We just need to go back to the original variable, and that's going to be an x squared minus 7 raised to the 7th over 7 plus c. The u to the 6 came from the original problem, because if this was a u, it was u to the 6th. Okay. So it's not too bad, right? Just a matter of picking the right u. That being said, though, I do recognize that, yeah, sometimes it can be kind of weird to know which one should be the u. But on the bright side, though, is even if you pick the wrong u, you're going to know in the problem. So it just means that, okay, this doesn't work. I need to pick another u. So let's practice with a couple more problems here. I don't know if I want to focus on. Yeah, let's do 3 and then let's do 4. 4 looks harder, or looks hard, but it's actually not too bad. So I'll let you guys take a look at this one here so you can copy it. We have the integral of 2t to the 5th minus 3 times t to the 4th dt. So let's take a look at this one. Again, kind of eyeball here. Okay, which one seems to be the inner function? But the thing about this one here in particular, actually, let's tweak it a little bit, guys. Because I would argue that we wouldn't even need to use the u substitution, Because if it has no power, we could probably FOIL, and that'd be easier. But let's tweak it. Let's say that it's to the... I know. Let's say that it's it's basically a square root. So let's tweak it a little bit to make it more interesting. Okay, so we have the square root of 2t to the 5th minus 3 times t to the 4th, where again, the t to the 4th is not inside. All right, so if you encounter a problem with a radical, as we will in the next couple of examples, the very first thing that I would always recommend is get rid of the radical by writing it as a power. So this is the integral of 2t to the 5th minus 3. And what is the square root? That's which power, guys? So we have basically the 1/2 power. Okay. So I do see an inside function is going to be our u. So I'll get here u is equals to 2t to the 5th minus 3. The du is going to be 10t to the 4th dt. Okay. Okay. Now let's get the dt. dt is equals to, divide by that, 10t to the 4th, divide by that, 10t to the 4th. So we get dt is equals to the du over a 10t to the 4th. Okay, so we get the u, we got the du, and got the dx. Now we can start substituting. So according to our values here, the substitution is looking like the integral of the u to the 1/2 power times t to the 4th, and the dt is being replaced here. And that's going to be here a du over 10t to the 4th. Again, the magic happens. I can cancel the t to the 4th. That's good. But now this problem is starting to look a little bit slightly different than the ones that we just did, because now the 10 is in the denominator and it didn't cancel with anything on the top. The numbers cancel on the other ones. This one here is not canceling. Is that a problem? Not really, because ultimately, remember that if you're dividing by 10, that's a constant, and that's the same thing as multiplying by 1 over 10. So we can simply rewrite this integral as 1 over 10. Okay, that takes care of the constant, times the integral of u to the 1/2 du. Okay. So if we're given this, then we're just going to get here a 1/10 times what is the integral of u to the 1/2. Remember, we added 1 to the power and divided by that. So we're going to get here a u to the 1/2 plus 1 over 1/2 plus 1, which should be a 1 over 10 times u to the 3/2. And again, with a trick that I showed you guys last time, if we are dividing by a fraction, then we put a 3 over 2, but the 2 just come to the top here. So it's 2 times u to the 3/2 over 3. Plus c. Now we are done. This is the integral, but it's in terms of u. So we just go back to the x's. So this is 1 over 10 times 2/3 times the u, which was 2t to the 5th minus 3 raised to the 3/2 plus c. Mhm. There we go. Thoughts or comments here, guys? What do you mean at the end? At the end at the last step? So going from here to here. Okay, so yeah, I just basically say, okay, well, everything stayed the same. The only thing that changed was the u, because the u was equals to 2t to the 5th minus 3. So all I'm doing is saying, okay, well, this was the u originally, but I'm just rewriting it back in terms of x. That's the only thing that changed. Notice the 1/10 stayed exactly the same. The 2/3 stayed exactly the same as well. But the u is the only one that changed. The c stayed the same as well. Just once you get a u, just go back to what you said the u was originally. So it's kind of like a double substitution. The first substitution is to replace the 2t to the 5th minus 3 as a u, which we did to do the integral. And once you get an answer, at the end, just say, okay, well, yeah, I did this with the u, but the u was technically 2t to the 5th minus 3. So we're just putting it back. So yeah, it's kind of two substitutions. And we'll keep on seeing more examples though, and hopefully it starts to make a little bit more sense. So let's take a look at number 4 here. Again, that's the one that kind of looks scary, but as we'll see, it's actually not too bad. Mhm. Okay. All right. So for this one, it looks like you have a lot of terms, but there is something that basically catches my eye. And that is the fact that I am racing all of this to the 7th power. So I see a power, then it's a good sign that I do have an inside function. So in this case, the inside function is the x to the 4th plus x cubed plus x squared. Again, because that's what you were racing to the 7th power. Okay, so if we spot our u, then I'll say here that u is x to the 4th plus x cubed plus x squared. Then the du is, let's see, the derivative is going to be 4x cubed plus 3x squared plus 2x dx. Okay, is that a good sign? Well, notice that the 4x cubed plus 3x squared plus 2x is exactly what we have here. So it is a very good sign. It just means that things will cancel nicely. So if we solve for dx, then we'll get that dx is equals to du divided by all of this. Okay. So we go ahead and rewrite. This is going to be, let's see. Again, we're saying that the u is the x to the fourth plus x cubed plus x squared. So that replaces our u. And it was to the seventh power times the 4x cubed plus 3x squared plus 2x. Now the dx substituted here. So times a du over 4x cubed plus 3x squared plus 2x. And it cancels. Excellent. Excellent news right there. Because now the integral that we are left with is the integral of u to the seventh du. And now it just became a problem where we need to use the power rule for integrals. So we're going to get here a u to the eighth all over 8 plus c. Now this is the integral, but it is in terms of u. We want it in terms of x. So we need to now back substitute the u. So this is going to be our u, which was x to the fourth plus x cubed plus x squared. And it was raised to the 8 and divided by 8 plus c. And that would be our final solution there. And so let's keep chugging along, guys. The more examples that we see, the better. Now let's try one with an exponential. And this is a problem that, again, if we were to see even a week ago, we would have no idea how to solve it. But now we can with the use of the u substitution. Now for this one, can you guys let me know in the private chat, which one do you think would be the u? Hmm. I'm seeing an x cubed. Any other takers for u? Okay, so an x to the fourth. All right, so we have these options right here. The u is x cubed or the u is x to the fourth. So let's try it with the x cubed first. And this is what I was saying before, that we might pick a u, and if it doesn't work, I mean, that's fine. We can just pick another one. And right now I'm going to test two possible u's. So if the u is x cubed, then the du is going to be a 3x squared dx. So then if I solve for dx, I would get a du over 3x squared. Now, if I tried with this one, then let's see, substituting things here, I would have an x cubed, so that was our u, times e to the x to the fourth times du over 3x squared. See, we substituting the u and we substituting the dx, but I still have a combination of u's and x's that are not canceling or anything. So I would say that this one, I don't think this u would have worked. Because even though I substituted everything in, there's still u's and there's still x's in the problem. You can either have all x's or all u's, no mix and matching. So this one here seems like it didn't quite work. So let me try it with the other u. If we let u equals to an x to the fourth, then the du is going to be 4x cubed dx. We solve for dx, and we'll get a du over 4x cubed. Okay, so let's try it with this substitution. Then I'll have the integral of x cubed times e to the u, then the dx, if we substitute it in, we'll get a du over 4x cubed. Okay, is this looking better? I think so, because at least I can cancel this x cubes. So now I don't have any x's. The integral is now looking like the integral of the 4 can get kicked out to the front. So it's 1 over 4 e to the u du. Okay. Now I only have u's, so we can perform this antiderivative. Now, how do we perform the antiderivative? Well, if we take a look at the formulas from last time, we see here, oh, the integral of e to the u du is simply e to the u plus c. So this problem is going to be 1 over 4 times the integral of e to the u du is simply e to the u plus c. But once we have the final solution, we need to replace the u with the value in x. So we're going to get as our final answer 1/4 e to the x to the fourth plus c. So again, guys, even if we pick the wrong u, that's fine. We'll see, though, that it's not going to work, so we can pick another one. Now, general rule of thumb, though, if you have e raised to an exponential, yeah, this is typically going to be the u, like 90% of the time, because that is the inner function. Okay, so now let's take a look at another one. But I'll let you guys try this one. at least for the startup. So what might be the U for that one? What's it, the U? And how does it look once we replace it? Mhm. Okay, so again, rule of thumb, whatever the E is raised to, that's generally going to be our U. Because then we can use the fact that e to the U du, the integral, is e to the U plus C. Okay, so let's see. If our U is a negative t squared, then the du is going to be negative 2t dt. Okay, solve for dt. And that's going to be du over a negative 2 t. So let's substitute. We're going to get the integral of t e to our u times dt. So if we substitute that, we'll get a du over negative 2t. Cancel, cancel. Great. I only have u's, no t's. So this is going to be a 1 over negative 2, or alternatively, simply a negative 1/2 times the integral of e to the u du, which is just going to be, put here, a negative 1/2 times e to the u plus c. And that's going to be a negative 1/2 e. What was our u? The u was negative t squared plus c. Okay. All right. So can you guys let me know in the private chat kind of how we're feeling? Hopefully not too bad. Again, we're saying this for the first time, so it's still a little bit weird, and that's perfectly normal. How are you feeling, Mireya? Okay. All right. So let's keep on seeing more examples again, because with the use substitution, they might come in very different forms. So I want you guys to see more of the problems that you might expect or you might encounter. Now, again, guys, so far we focus on, in general, if you have something raised to a power, that is typically your u, the inside function. If you have radicals, whatever's inside the radical, because it's the same thing as something inside a power, it's the 1/2 power. In the case for the square root, then again, that's typically your u. The examples that we saw right now was problems with exponentials. Typically, the exponent of the e is the u, as we saw in these two examples. So now I wanted to show you other types of problems where the u is, again, most of the time in problems involving fractions, the u is going to be the denominator. Again, most of the time. So let's take a look at example 7 and 8. Hmm. So for this one, we have the integral of 5 over 5x plus 7. So I'll just put hint. Denominator is usually the u. And again, guys, I mean usually, not 100% of the time, but pretty frequently. All right, so I'll let u equals to the 5x plus 7. What's going to be the du? The derivative of 5x plus 7 is simply 5 dx. So we solve for dx, and we get a du over 5. Okay. So we got the u, we got the dx. So now let's start substituting in. All right, so this problem is going to be the integral of 5 over u, substituting in the dx. That was du over 5. Look at here, 5's cancel. So we have the integral of 1 over u du. Now that one might be tempting to use the power rule, but this is a formula, guys, or it's a rule that's already established. Again, if you take a look at the beginning of the notes, I said that whenever you have 1 over u du, the integral is going to be the ln of the absolute value of u. So going back to this one, 1 over u du is the ln of the absolute value of u plus c. Okay, so this is the formula. So this integral is going to be 1 over, I'm sorry, it's going to be the ln of the absolute value of the u plus c. Now, what was the u? Well, this is going to be the ln of, our u was 5x plus 7. Plus c. All right, so let's take a look at one more here. And then we'll try another type. Well, we're kind of seeing all types already, but we're going to put in a twist on the next couple of ones. Namely, when we have a definite integral, because so far we worked with indefinite integrals. That's why we've always been adding the c. But in the examples that we'll see in a second, those are going to be definite integrals. But in the meantime, though, let's take a look at this one that, again, might look kind of weird, but I don't think it's too bad. Okay. Alrighty. So again, usually the denominator is a u. So I'm going to see if this denominator works. So u is equals to 4 plus e to the x. Let's see what's going to be the du. What is going to be the derivative of 4 plus e to the x, guys? Very good. Excellent, excellent. The derivative is e to the x. Is that good news? I think so, because I do see an e to the x here. So it's a pretty good chance that they will cancel. So just put here the x. All right, so we get the dx. And that's going to be equals to du over e to the x. All right, so let's start substituting things in. So we have the integral of e to the x all over. And again, we said this one here was the u. That the dx is du over e to the x. Once more, we can cancel them out. So we're left with the integral of 1 over u du, which is the ln of the absolute value of u plus c. And at this point, we are pretty much done. All that we need to do is replace the u. We're going to get the ln of the absolute value of 4 plus e to the x plus c. Thoughts, comments here, guys? Okay. So let's continue on. All right, now I'm gonna, well, yeah, I'm gonna go into, well, let's just do this one, and then we'll take a look at the definite integrals. So last indefinite integral, we have the integral of the ln of x squared all over x. Whew. Alrighty, so for this one, looks kind of weird because we have the ln. But again, if I were to ask you what seems to be, well, I guess it, yeah, that one, this one here is, I forgot if there was a typo. You can still do it, but well, we can try it. So if you were to take a look at this one, what do you think might be a good choice for you? I'm thinking that, I don't know, the x squared, for example, kind of looks like it, right? Because the x squared is inside. So let's see. All right, so if the u is x squared, then the du is 2x, which might show a little bit of promise because there's an x here, but it's an x in the denominator. So I'm not sure if this one's going to work. Because if I solve for dx, then I'll get a du over 2x. So if I try to simplify it here, I have the integral of the ln of u. We substitute in the dx, which is du over 2x. But notice that we still had an x on the bottom. So this one here it doesn't quite work because I got x's and I got u's. Okay, so this one didn't quite work. So let's try it with another choice of u. I'm thinking that, okay, well, maybe the ln of x squared. I don't know. Let's see. Maybe it works, maybe it doesn't. So what is the derivative of the ln of x squared? And again, remember, guys, the derivative of the ln of x or the ln of u is 1 over u times the derivative of u. All right, so in this case, the derivative of the ln of x squared is going to be 1 over the inside times the derivative of the x squared. That's 2x. So our du is equals to, going to cancel one of the x's here. So it looks like it's 2 over x dx. And now we tried the x squared, but right now we're trying the ln of x squared. So basically we said, when we said that this one here was our u, it didn't quite work. So I'm going to be seeing if I try a different u, will it work? And it kind of looks like it might work. Because once I took the derivative for the ln of x squared, we got this. And when we solve for dx, let's see, we can multiply by the reciprocal by an x over 2, multiply by an x over 2. So we get an x over 2 times du. So let's see if we substitute it in, will it work? We'll get, remember the ln of x squared, we said it was u. Over x times the du, which is x over 2 du. I can cancel the x's now. So it looks like this u worked. And we'll get the integral of 1 over 2 u du. Okay. So we do the antiderivative, and it's going to give us a 1/2. If it's the integral of u du, we add 1 to the power and divide by the exponent plus c. So our final answer is going to be 1/2 times the u, which was the ln of x squared over 2 plus c. Okay, so this one here is probably the weirdest one. But again, it's this matter of testing use to see which one actually cancels things out. Okay. Alrighty, guys. So let's go ahead and try one. Yeah. let's go ahead and try one that now has limits of integration. Now, the good news is that it's not going to be all that different. We still need to select the u, but because it is a definite integral, remember we will need to evaluate at the limits of integration. So for this one here, there's two ways of handling these problems, and I sometimes see that students kind of prefer the second approach. So I'm going to show you both approaches right now so you guys can compare them. But the whole idea here is once we're given a definite integral where we need to use a u substitution, we're going to need to change the limits of integration. And I'll show you guys why in a second. But first, though, if you were to take a look at this problem, again, I have a radical. We don't like radicals, so we rewrite them as a rational exponent. So this is the integral from 0 to 1 of 12x times 1 minus x squared raised to the, if the root is 5, then it's 1 over 5 dx. Okay, so that is the integral without any radicals. Now, if I were to ask you guys, okay, well, if you wanted to select the u, what do you guys think the u might be? It's going to be the inside, the 1 minus x squared. Okay, then we go and find the du. So the derivative of 1 minus x squared should be a negative 2x dx. We solve for dx. And this is going to give us a du over negative 2x. Okay. So if I go ahead and do that, then I'm going to have the integral of 12x times our u to the 1/5 and we substitute in the dx, and that was du over 2x, negative 2x. Okay, so it's showing promise. I can cancel the x's. Then I have essentially a 12 divided by negative 2, which I'll factor it out because they are constants. So put 12 divided by the negative 2. And now we have the integral for u to the 1/5 du. Okay. Now, at this point, we haven't done anything different. But notice that I did not write the limits of integration right now. So right now, what we're saying here is that we are integrating with respect to u. And when we were integrating with respect to x, what this integral was telling us, hey, you're integrating as x goes from 0 to 1 for the antiderivative. So could we be able to say that, oh, x is going from 0 to 1 in this integral? Well, do we have any x's? Do we have any x's in our integral? Not really. So how can we know? I mean, because if x is changing, that's fine, but I don't care about the x's because right now I'm caring about the u's. So we need to change the limits of integration to match the u. To be more precise, the changes in u. Now, is that a complicated process? Not really. This is what we're doing basically. The bounds right here, which were originally 0 and 1, what they're going to be now is going to be, because again, well, what they're going to be now is the value of u at 0, the value of u at 1. Because remember, this u's that we're selecting, they are functions of x. That's how we see the u is 1 minus x squared. So let's figure out what is the u evaluated at 1 and the u evaluated at 0. Okay, so what is the x? I'm sorry, what is the u when x is 1? It's going to be 1 minus 1 squared. So that's what? 0? And the u at 0 is going to be 1 minus 0 squared. Oops. Going ahead of myself. So this one here is actually 0 and 1. So this gives you the new bounds. We're performing this antiderivative going from the u values of 1 to 0. And again, these are the u values, not the values for x. That kind of makes sense, guys? And so this is the first approach. I'll show you the second one in a minute. But let's finish this problem. All right, so once we've rewritten the integral in terms of u's, once we've rewritten the limits of integration in terms of what's happening with the u, not the x, then we just go ahead and do the antiderivative. So this is going to be, let's see, 12 divided by -2. That's going to be -6 times, let's see, what is the antiderivative of u to the 1/5? Let's see, u to the 1/5 plus 1. What is that? 1/5 plus 1 times 5 times 5. So this gives us what, 6/5? Okay, to the 6/5. And with the trick, it's 6/5, but the 5 just multiplies here. And we're validating that as the u, or the u is equals to 1 and 0. Now, at this point, I'm also going to cancel the 6's. So we're dealing with -5 u to the 6/5, and we're evaluating that at 0 and 1. So this is going to be then -5 times 0 to the 6/5 minus 1 to the 6/5. Mhm. Okay. So 0 to the 6/5, that's 0. 1 to the 6/5, that's 1. So it looks like we have -5 times -1, which is 5. And this is our solution. Notice that in this problem, we didn't need to go back to the axis. We kept everything in terms of use. Now, this is going to be the other approach, guys. And again, this is typically what the students prefer. Alternate approach. Let me write down the original problem. Well, let me basically start off. Well, let's write the original one. The original was the integral from 0 to 1 for 12x times 1 minus x squared to the 1/5 dx. This was the original. Now the alternate approach pretty much continues as normal. We define the u. We got the du. And we got the dx. So nothing different there. We do the integral, but this is what I will ask you though. If you're using the alternate approach, when you're writing the problem again, leave the bounds empty. Just empty for now. Okay, because we're going to be putting them back, but at the very end. So we had here a 12x times the u to the 1/5. And once we plug in the dx, it was a du over a -2x. And yeah, we cancel the x's. We divided the 12 by -6. So this one here was a -6 times the integral of u to the 1/5 du. And again, I'm leaving the bounds empty, keeping everything the same, pretending it's not a definite integral. We do the antiderivative for this one, which we saw right now that it was -6 u to the 6/5, if I'm not mistaken, over 6/5. And we cancel the 6's. So we're left with just the -5 u to the 6/5, which is a -5. Okay, now this is where it's different, guys. Or this is now where we're actually putting in the bounds. When we were doing the other problems, I said, hey, once you get the antiderivative in terms of u, just replace it with the x. So let me write it here. When you go back to the x, bring back the limits of integration. Okay, so now that we perform the antiderivative, we have a -5 u, which was 1 minus x squared, raised to the 6/5. And now that we went back to the x's, Now we include the bounds, which were 0 and 1, I believe. Yeah, 1 and 0. No, 0 and 1. So again, guys, only after you perform the antiderivative and we go back to the x's, that's when you include the bounds. Will our answers be different? Not at all, because we're going to get the same value inside the parentheses. We're going to have a -5 times 1 minus 1 squared raised to the 6/5 minus 1 minus 0 raised to the 6/5. Now, why is it the same thing? Because notice, we already did this operation 1 minus 1 squared. If we use the other approach, we did this right here. We did it at the beginning. The difference with this approach is we're doing it at the end, because this is still a 0 to the 6/5 minus a 1 to the 6/5, which again, it's exactly what we had here. 0 to the 6/5 minus 1 to the 6/5. So this ends up being a -5 times 0 minus 1, which is 5. So let me compare the two methods. Again, it is really the same thing. The only difference is with the first approach, we switched the limits immediately. So we didn't need to go back to x's. But if we do it with the second approach, we do the antiderivative, the integrals. Once we get a value in terms of u, we go back to the x's, and now we bring down the limits of integration, or we incorporate them again.